How's it coming so far, though?
Any troubles or what? Not so much.
All right, very good. How's it going? Good? All right, good. Good to hear. How's it going with you, Shafan? Good? Good, good. You want to meet after office hours today?
Yeah, no, it's thank you.
After 2?
Yeah.
Okay, yeah, good. Oh, that's right. I'm meeting with Action today, huh? Very good. How are you? Good morning.
So I had some trouble opening the assignment. It's not in the readable format.
Really?
Yeah, I've been trying it all over the weekend, but I was not able to open it. Is there any other way I can access it?
The homework, right?
Yes.
I'll email it to you.
Okay.
It's a PDF. It should be able to. Have you guys had trouble opening it? Anybody? No? Okay. I can print it and give it to you physically if maybe there's a problem with your PDF reader.
I tried it in every single friend's laptop. Oh, okay, then I'll just take the PDF from it.
Okay, okay, great.
Thanks.
Let me know if you continue to have trouble. I can make arrangements to get it to you a different way.
Okay, I'll keep a note during the next assignment.
Sure.
Okay.
Anybody having trouble with the homework? You guys doing it all right?
I have a question.
Sure.
You said Elliot's notes, something about cylindrical system.
Yes, they're uploaded in the reading material.
Sorry, so is that the second one? I just don't know which one. Right, they're not labeled by anybody's name, so the second guess.
Really? Okay, good point. Good point. So let me make a clarifying remark about that. All right. Okay, so for the homeworks, let's see here. Number 2. Where does it say Elliot's notes? Let me see.
For the third question.
Third. I see, yeah. Okay. Yeah, those are the generalized coordinate notes. Yeah, so those the book chapter that I put at the as an upload is from his book.
Okay.
So let me go to let's see. Reading material. This generalized coordinates handout here. This is from his book. So these are Elliot's notes. Let's see. Why isn't it downloading? All right. God. All right. Okay. So yeah, those are Elliot's notes. The generalized coordinate handout, the second one. Very good. All right. Okay, so it's about time. Let's go ahead and get started. Let me pull up this in case any of the online students have questions. So, all right, so let me know if you guys have any trouble with your homework. We have an office hour today after the lecture, starting at 11:30 to 12:30. And if you have questions, please come into my office. And the homework is designed to really make you understand the concepts a lot more, right? So as you work things out, you'll notice some things might be just copied from the notes or whatever, but as you write it out in your own words, you understand it more. So it's good to do that. And throughout the course, we're going to do a lot of homework, 7, I believe. And by the end of that, you should really get used to writing out derivations and doing calculations, which will be really helpful when you get to graduate studies and research. All right. Okay, so come by my office hours. Anyone who has is online, is an online student, I will have Zoom open in the office hours. You can get to that link from the Canvas page, and I'll be able to answer questions on that. All right, great. Okay, so what did we study last time? We got into lecture 2, and then here we're looking at convection current density. So the first thing we wanted to do is define what we mean by a current density, right? We have some flow of charges. In this case, we assume that there's a charge density that's mobile. It's moving through space at some velocity. A charge density moving through space at some velocity through some surface area delta S. We're able to define exactly what we mean by current, right? Here we said current, a change in current, or the calculation of the current is equal to the limit as delta T goes to 0 of delta Q by delta T. The amount of coulombs that move through a surface in per unit time, right? Coulombs per second. But then we notice that delta QE, delta T, this is the total change in charge over the total time. We have the charge density. We can rewrite this quantity, delta Q over delta T, as the following, which we did in the first derivation. We end up finding that the current density can be written as the charge density, whatever the density of charge that we're considering as calculating the current from, the velocity of that charge density, and through a surface area delta S. So this is an infinitely thin, uniform, infinitesimal cylinder, like a filament of current, and that charge density is flowing down through this filament at velocity v through some means, and it passes through this surface area delta S. So what are we doing? We're calculating, we're counting up all the charges that pass through this surface area delta S in a given amount of time, right? The charge density multiplied by the velocity gives you, this is coulombs per meter cubed, and this is meters per second. So then after this product, we have coulombs per meter squared second, and then we multiply by the area, we get coulombs. So it's just in coulombs per second because of the second left over from the velocity. So you get amperes, right? We want to calculate a current density now, where we can define the density of current at any given point as a continuous vector field. So this vector field now here is a new vector field called J, and that vector field we divide by the area. So it's now amperes per meter squared. This has a definition, so you give me an x, y, I give you a vector. That vector defines the current density at that point, and it's only defined for the cross section of this cylinder, right? Outside, that vector field takes on a value of 0, if we're assuming that the charge density is confined to the cylindrical filament.
That's the point.
Yes, so you can define at every given x, y, and z in a continuous fashion a density of current, meaning this many amps. 4 amps per meter squared, for example. And then if I had a unit area or a 1 meter by 1 meter area and I passed that density through it, I would pick up 4 amps, right? Which is so many coulombs per second. Okay, good. So you can do that in a vector sense and you get this new vector field J. All right, then we wanted to restrict our attention to conductors, so not just to charge cloud floating, but to conductors. When we looked at conductors, we used Gauss's law and the charge continuity equation to define a expression which defines what happens to a charge density when we impress it into a conductive medium. If this conductive medium has conductivity sigma, then we will see that this charge density decays very rapidly, right? And the amount of decay we characterize, or the time it takes to decay, we characterize by what's called the relaxation time. The relaxation time is the amount of time it takes for the charge density that was initially placed to decay to e to the -1, right? Same as a time constant. Okay, and what we noticed was the charges are going to move to the surface of the conductor where they're no longer able to move. They're trapped. There's no more conductor for them to go. And when they get up there, they distribute themselves in such a way that the total electric field inside the conductor is 0. So we have this applied electric field. It's a static field at this point. We're talking about static conductivity. The applied electric field exists omnipresent. I place the conductor in the static electric field and the dynamics happen. The charges move to the surface. And once they arrange themselves in such a manner that there's an electric field induced inside of the conductor, which is exactly the right electric field to cancel the applied field within the volume of the conductor, because we must have 0 electric field in the conductor for infinite conductivity. Yeah? Great. All right, then we defined what do we mean by conductivity, right? So we said that there's some charges now. Now there's a force applied across the conductor. The charges are moving in response to this force. The force is the electric field. The charges move in the opposite direction of the applied electric field, and they move with a particular velocity that we call the drift velocity. In reality, this drift velocity is very slow, all right, centimeters. It's very, very slow. You can do the calculation to find how slow it is, but it's much slower than the speed of light, of course. There's a proportionality constant that tells you the velocity with respect to the applied field strength, and that is called the mobility, all right? So this allows us to define what the velocity is. Once we have the velocity, we can go back into our equation where we defined what the current density was, and we can replace this electron charge density, the velocity with negative mu times E, right? And then we can lump this quantity, which is the charge density multiplied by the mobility, into a parameter we call the static conductivity. So that's what the static conductivity is, right? That's what it means. That's what this constitutive relation means. J equal to sigma E, right? It means if I apply an electric field across a conductor, what is the current density that's generated? This is a proportionality constant, right? For a given electric field, this constant tells me the strength of the current density induced, right? And how is this derived? What does it mean? Well, it means that I have a particular charge density and the metal or whatever conductor we have provides a particular mobility, and these two together constitute the conductivity, right? So I have a charge density, the mobility that the conductor allows the charges to move, the drift velocity, defines the conductivity. So different metals that have different mobility or different conductivity will generate a different current of course, with an applied electric field. Okay. So then we started talking about dielectrics. And dielectrics here, we have a different story. We don't have charges that are free to move about the conductor or the lattice, right? Before we had donated charges from each of the ion or each of the atoms in the conductor that allow for there to be a free charge density, which we call the electron C. Here we have what are called bound charges. So in ideal classical model, we have an atom which makes up a material. That atom has a positive nucleus and a negative electron surrounding that atom, orbiting it, right? If there's no charge, then we assume that the atom is so small that the negative charge and the positive charge have their center of charge, if you will, or center of mass of the charge density to be coincident, so that we get no electric field generated, right? Net charge is 0. If you don't have any positive and negative charges separated by some distance, then you won't have an electric field generated between them, right? When I apply an electric field, an external field EA is applied to the material. What happens is the negative charges want to go in the opposite direction of the applied field. The positive charges, we're assuming, are nuclei, they're heavy, they're fixed. So therefore, the electron orbit becomes stretched and elongated into an elliptical path. Because that happens, we displace the center of mass of charge of the negative charges and the positive charges, and we can define a separation of charge. Once we're able to do that, we know that an electric field will be generated in between those charges, right? Stored energy. If I have a spring, right, and I stretch the spring, then I've stored energy in the spring. If I let go of the spring, it will return and it will give me that energy back, right? Same thing with this. If I apply an electric field, I stretch that electron cloud, I've stored energy in the distortion of the atom's orbit. And then if I let go of if I turn the electric field off, that charge will return. But the energy that I've stored in there is in the form of the electric field generated between the charges. It's stored in the electric field, right? Energy is in the electric field. We'll see that, or we saw that in lecture 1. Integration over the volume of epsilon magnitude of E squared, dV, energy density. So we store energy in the form of an electric field. We can get that energy back as soon as we remove the electric field. This is all statics right now. Here we have, okay, so we need to quantify these distortions. We're going to call them dipole moments. So here we have the separation of a plus and minus charge. We can call that a dipole, right? A dipole is defined as that. The dipole here we're going to call dpi. The ith dipole is defined as the charge q into the length, the classic definition for dipole, right? Electric dipole. Okay. What we have to remember is this vector here that quantifies or characterizes this dipole moment. L goes from the negative charge to the positive charge, which is a little bit counterintuitive because normally the electric field points from the positive charge to the negative charge. So just be cognizant of that. All right. So here we have a material with no applied field. There will be no dipole moments induced in the material. Here we have a material where we apply an electric field and we see that dipole moments are induced in the material, a number of them, right? Instead of calculating the response, so now we have dipoles. What do we know about statics or the last class you took in electromagnetic theory? When we have a dipole, we can calculate the potential field due to that dipole, right? We're going to do that in the next slide. You can calculate the electric scalar potential, V, right? Everywhere in space, a scalar field V. You can calculate that everywhere in space given a dipole, and you guys have done that, I'm sure. So we could either, at this point, let's say, this point here, I want to calculate the electric scalar potential. Why are we talking about potential? Because we're talking about statics right now, right? This is applied electric field that doesn't vary in time. So at this point, I want to calculate what the electric scalar potential is. I could add up the electric scalar potential due to all of the dipoles in the material, right? That's a brute force way to do it. But the problem with that is there are so many dipoles and you must also know their relative positions and orientations, and that is impractical. Instead, we don't need to know this granularity where each of the dipoles are accounted for individually. What we can do is define a new field, a new vector field P called the polarization field. And we're just going to average a bunch of dipoles per unit volume and generate a continuous vector field out of that. And we're going to use that to account for all of the dipoles. All right. So what is this vector field P? It is the sum of all dipole moments in a given volume. And then we divide by that volume and let that volume shrink to 0. So we can define it at a point. So we can make this vector field P a continuous vector field. You give me this point in a material, X, Y, and Z. I will tell you what P is there. It's a vector field. It has a direction and it has a magnitude. And I calculate that by taking some volume and shrinking it down to the point and calculating the number of dipole moments per unit volume, right? As this limiting process. NE, the number of atoms per unit volume, multiplied by the volume is the index that it goes up to, all right? That's the number of atoms, right? The density multiplied by the volume gives you the number of atoms that I need to sum up within a volume. I add up all those dipole moments, take the limit so I can define it at a point, and then I have a continuous vector field in the form of an average of a set of discrete dipoles. I can calculate the response, whatever I want out here, using this vector field P much easier than I can if I had to sum up all those dipole fields, right?
Definition, summing up all those dipole fields?
Yes, summing them up. Discrete.
So we're exhaustively summing up to avoid exhaustively summing up.
Okay, this is a definition where we're going to utilize the concept in the definition. We're not going to physically sum up the dipoles, right? This is a measured quantity. We'll see. Ultimately, you have to measure this quantity. It is an analytic model, but to calculate, given a material, I'm sure you probably could, but it's not technically or typically done. Good question, though. So let's look at this polarization field a little bit deeper. How do we find the polarization field P? We assume an average dipole moment, right? So different parts of the material might have a different dipole moment than another part, right? We could have a different length of that dipole than over here. We don't want to rigorously account for each of those dipole lengths. What we want to do instead is assume that we can average over a volume. That's a classic concept in metamaterials, metasurfaces, and even in electrical engineering here, or electromagnetic theory. We want to average over some volume the microscopic properties and derive a macroscopic property out of it that we can use easily in our macroscopic Maxwell's equations. So here we have dpi, which is dp average, we're going to call it now. We're going to say that's q times L average, some average length, right? The electric polarization vector can then be written. Okay, we go back to the definition of P and we plug in our new average definition for dpi. And what do we get? NE dp average, which is NEQL average. So now we have some number, right? Number of dipole units, dipole moments per unit volume, and average length now. All right? Okay. Now, let's define, okay, so far we've developed this vector field P, and I've been telling you that P makes it easier to calculate the response of the material or the contribution of the material to the field, right? But how do we do that? So let's utilize our definition of P to find what we're going to derive is the concept of permittivity, right? So the field at a point R, due to an electric dipole at the origin, can be found using the magnetic vector potential. And I understand we haven't gone over magnetic vector potential yet. We will in this course, but I'm sure you've heard of the concept in the previous course, the prereq, right? So we have some dipole moment. We have some electric dipole here, right? That has plus Q and minus Q. It's at the origin. And I want to find at some R, I want to find what V is out here, right? V at R. Okay, so this is the classical formula. 1/4 pi epsilon naught P dotted with R minus R prime over R minus R prime cubed. Okay, let me look at this. I don't think this is magnetic. I think this should be electric. Make that change, all right? It's not the magnetic vector potential. We're not talking about currents. It's the electric scalar potential even. I don't know why I have that there. Must have been a typo when I was making these notes. Okay, good. So what do? This is a classical formula, right? This is how you calculate the potential due to a dipole. All right, so this generalizes when we replace P by PdV. And what do we mean by that? So P is one dipole, right? A dipole, electric dipole. PdV. P is the number of dipole moments per unit volume, right? And if I multiply by a differential volume dV, then I'm going to get dipoles again, right? So we generalize it by replacing P with PdV. PdV is P, right? And we integrate over some volume. So that's what we've done here. We're going to integrate over the volume, and we now have P here. So this is due to one dipole. This is due also to sort of a continuous distribution of dipoles, but we're also assuming that PdV is equal to, so PdV is the dipoles that you would get at a particular infinitesimal volume. And we're going to add all those dipoles up to get those electric scalar potential at some point R in space. All right. So here, R minus R prime divided by R minus R prime magnitude cubed can be written as the gradient prime of 1 over R minus R prime. All right. This you can derive easily to prove it to yourself. If you just take the gradient of this function, you get this. All right. Okay. So what we can do is we can substitute that in now. So we have P dotted with the gradient here now. And what we can do here is use a theorem, which is the product rule here. So the divergence of P over R minus R prime minus the 1 over R minus R prime times the divergence prime of P. So that comes from a vector identity that you can get in the lecture 1, right? Yes?
Do you have any tips on like how to avoid confusing like electric potential and volume?
Okay,
Like you said,
yeah. That's a very good observation. There is an overuse of notation here, right? Then normally it would probably switch to phi here. So there's, okay, yeah. So you either have to be cognizant about how you've written it, or classically this could be a lowercase v, which would probably be a little bit, you could do that. Or v is sometimes replaced by phi. So electric scalar potential is sometimes phi. But that's a good observation. Yeah. If this was like a manuscript we were writing, I'm sure we would have caught that and probably changed it to like phi or added a note after the equation.
Yeah.
Good.
I think I understand what I'm looking at here. I just wanted to,
Yeah.
I'll confuse myself in my notes.
Yeah, it's great. Yeah, very good.
Level prime instead.
This gradient.
Spatial derivative.
Yeah, so remember, okay, so here, look, we have gradient prime is equal to, or it's defined as, partial by partial x prime plus partial by partial y prime, partial by partial z prime, z hat, right? And then this r minus r prime, you can say r is, is x hat, y hat, z hat. And r prime is equal to x prime x hat, y prime y hat, z prime z hat. If you write all that out and do the derivatives, then you can derive this expression. All right? The prime just means I'm differentiating. Remember, upside down triangle is nothing but spatial derivatives and differentiating with respect to spatial coordinates for the source, the prime coordinates. Okay, let's apply the divergence theorem to the first term. And we can convert the first term into a surface integral. So we have these two terms now. The potential is due to two different terms. The first term is a surface charge density. It only exists on the surface. We take the dot product of P with ds. So P is going to have a value everywhere within the volume and on the surface, right? But right outside the surface, P is equal to 0 because the number of dipole moments per unit volume, and we're assuming that the electric field that induces the dipoles is also existent outside the material, but there's no material there to polarize. All right, so P is defined everywhere, but it's 0 outside of the material. So right on the surface, P dotted with ds gives me the potential due to the dipoles or the surface charge density we'll see it's related to at the surface. And here we have a volume charge density, right? This is the integration over the volume. So the dipoles in the volume and the dipoles on the surface. So the potential due to a surface charge distribution, this term can be considered, on S of P dotted with ds. So we define, if you look at the form of this equation, right? If you remember electrostatics, the electric scalar potential is 1 over 4 pi epsilon naught times Q over R minus R prime, right? So we can say P dotted with ds is like a charge. It has the same form, right? P dotted with ds has to be a charge. This is a potential, and this is the rest of the equation. So P dotted with ds is sigma b. We call it sigma b because b is bound. The charge is bound. It cannot move. It's bound to the atom, right? ds or sigma B is equal to P dotted with N. All right. So if you take the dot product with the outward normal on the surface of P, then you get the surface charge density. That surface charge density contributes to the potential anywhere in space. There's another term, which is 1 over 4 pi epsilon naught, 1 over r minus r prime. Then we have this. This must also be some kind of charge, divergence prime of P, right? To fit the form of the equation for potential. So potential due to a volumetric charge distribution. Rho bound. Sigma, we usually use this. Sigma, we use the notation of the symbol sigma for surface charge density, and rho we use for a volume charge density, right? Classically. So that bound charge density is coulombs per meter cubed, because it's a volume charge density, minus divergence of P. And here we have coulombs per meter squared for the surface charge density. All right, good. So what have we done? We have taken this vector field P that we've defined, which is accounting for all the field due to all the dipole moments that are polarized in the material. And we found the potential anywhere in space due to what we're defining now as a surface charge density and the volume charge density of minus divergence of P and P dotted with N on the surface. All right. So we found these equivalent surface and volume charge densities that we can calculate the potential now. And these are the potential due to a bunch of dipoles in a volume, right? So we found a way to derive equivalent charge densities, which we know exactly how to find the potential due to by using basically the mathematics of vector calculus, right? Macroscopic, yes. Good, okay. Let's define a little bit more. We're almost to the permittivity. So, yeah, sure.
So the point R would be inside the surface or outside?
Anywhere, yeah. It could be anywhere. Good question. So to account for this charge density, we're going to write the charge distribution in terms of free and bound charges. Rho B we know are bound, right? They're bound to the atom. They cannot leave the atom. Rho free are free to move about the lattice, right? So in general, the charge density, the total charge density is going to be comprised of free and bound charges. All right? Okay. Now we can go to Gauss's law and we can write it in terms of the physical measurable field E. Okay, so the divergence of E is rho free. Okay, so remember, divergence of D is equal to rho, right? But now we're saying this is rho free plus rho bound, right? If we divide by epsilon naught both sides and factor it out, okay, so this D is equal to epsilon E, right? Let me write it out. So divergence of epsilon E equals to rho free plus rho bound. What am I assuming about epsilon when I factor it out and divide both sides by it? Not isotropic, close though. Homogeneous, right? It does not depend on position. This is the derivative. Upside down triangle is nothing but spatial derivatives. It's like partial by partial x. If I pull out something out of a partial by partial x, that means that it's a constant with respect to x, right? Okay, so we do that here. All right, so we have rho free. We know what rho bound is. Rho bound is the divergence of P minus the divergence of P, right? Okay, so rearrange this and multiply through by epsilon. So what have we done here? We've multiplied back by epsilon. We remove, okay, so here, I'm gonna do it here. Divergence of E is equal to, okay, so before I do that, we'll throw this term to the other side. So minus, okay, so epsilon, and then minus the divergence of P, should be plus. Rho free, right? And now what I can do is I can basically distribute, the divergence operator is distributable. So I can say this is the divergence of epsilon naught E plus P is equal to rho free. Good. Okay, so we have the divergence of something is equal to a charge density. And we know Maxwell told us that the divergence of D is equal to rho, right? So we can define this new vector field. Okay, so before Maxwell told us, what we're saying is we have the divergence of some vector field. Adding two vector fields gives you a vector field, right? And this goes back to your question about whether it's inside and outside. Epsilon naught E is the applied field, basically, right? And P is the contribution due to the material. So if it's inside, you add these. Okay, epsilon naught E plus P, we're going to define a new vector field D, right? It's a mathematical construct. We're going to define it so that we can get to a Gauss's law here, divergence of D equal to rho free, which is valid in media or free space, right? So here we get a Gauss's law, which is also valid in media. In contrast to the one above, this version is written in terms of the new non-physical vector fields D, right? This is Gauss's law without considering media. Divergence of epsilon naught E is equal to rho. It's written in terms of D, right? We introduce D to introduce materials. So this new vector field D is like E, it's like epsilon naught E, but it has a new contribution P, which is the contribution to the electric scalar potential due to dipole moments that are induced in the material media. All right?
So with vacuum permittivity, should we interpret it as the vacuum itself is polarizing?
No, I mean, you don't want to think about that. You want to think about epsilon naught being a factor that can convert E into a density only in vacuum. All right? It's a constant that makes E look like a density, a flux density. P you add to that whenever you're in a material. Yes.
Can some sort of build its dielectric dipoles and polarization? Are they the same?
Due to electric dipoles, yeah, polarization is the presence of the electric dipoles. Yeah, this might be bad. So instead of this, say AKA, polarization. Yes, good catch. So here, what do we notice about divergence of D now? Divergence of D is only talking about free charge densities, all right? Free charges. So whenever you use Gauss's law, let's say you wanted to try applying Gauss's law to a polarized material. If you apply Gauss's law to a polarized material, you might think that there's some charge inside, but that doesn't apply, right? Say I put a Gaussian ring around this top plate where this dielectric is, for example. And if I did that, I might think that there are free charges there, so there must be an electric field, right? But there won't be, right? Because this divergence of D is only talking about free charge density. Remember that. Yes.
Does that mean that like in free space or in a conductor, there are no bound charges?
In free space, there are, okay, so when we say free space, we're talking about vacuum, right? And we're assuming vacuum has no matter. Electric fields can be in a vacuum with no matter, right?
Okay, yeah.
So in there, we have no bound charge, no polarized atoms, right? And so that's what's meant by that, right? So divergence of D would be 0 there, right? Okay. Good. So let's see what happens with this picture when you polarize. Here's a picture. I think we're going to dig into this next slide. But I'm applying a potential, a battery, this is DC, a scalar potential across a parallel plate capacitor. So on this part, the positive charges leave the positive terminal of the battery. They go and deposit themselves on the plate, right? So there are positive charges here. Negatives do the same on the bottom. Now, because these positive and negative charges are separated by some distance that they cannot cross, then there is an electric field generated. So I store energy in the capacitor in the form of an electric field, same as I do when I stretch an atom, right? Okay. Now, so E applied is here, right? If I have the right half side, where I have a dielectric material with a non-zero permittivity or non-unity permittivity, placed in the material media between the capacitive plates, then what happens? We still have E applied here due to the charges that were placed on the plates from the battery. What we also have is induced that E applied will be applied throughout the volume of the dielectric. We'll polarize all the atoms. We can generate a P, a vector field P, and we'll see how that vector field P manifests itself. So what will happen is, I don't know if I have a picture like that. Okay, what happens is, here, So it induces dipole moments, right? Now these two, so one atom is this part, another atom is this part, another atom is this part, right? But if you look at this, what you'll notice is these two cancel out and these two cancel out. These positive and the negative of this, the previous atom, and the positive of the atom before it, those two will cancel out. They tend to cancel out in a macroscopic classical model. All right. What's left over is this charge and this charge. So when you polarize a uniform dielectric, it needs to be a uniform material. When you polarize a uniform dielectric, the internal charge density goes to 0 because neighboring atoms. So here's a positive nucleus. Here's a stretched electron cloud, right? Now, the next one down here is going to have its negative charge stretched down, but the positive is still there, right? And the negative of this one is overlapping in a classic macroscopic sense. So all of the internal charge cancels, and you're left with bound surface charge only. The surface charges, all right? So let's take a look at those surface charges. So what happens? We have surface charge only, a positive and a negative, right? Okay, the polarization field is the induced electric field due to this surface charge because it's a uniform dielectric. Why does it matter if it's uniform? Because the divergence of P will be 0 if it's uniform, right? The volume charge density will be 0 if it's uniform due to this cancellation. All right, so we have the P field, which is generated from the induced charges that end up only existing on the surfaces of the dielectric because the internal charge is all canceled. What do you notice about this P? What is awkward, or what is confusing about it? Maybe not confusing, but what is striking about it? Yeah, by construction, that's important. But is that what you would expect? Yeah, so here you have positive charge and negative charge. And we know that electric fields start from positive charges. They emanate from positive charges. Divergence of D is equal to rho. So if rho is positive, then the divergence of D is positive. When you have a positive divergence, that means it's a source, right? There's flux leaving that volume. So D, lines of D, will source from, they'll leave positive charges, right? And then when the divergence of D equal to rho, where rho is negative, it's a minus charge, then the divergence is negative, which means it's a convergence, which means it's a sink. So electric field should start from positive charge and terminate on negative charge. But here, remember what I said before, we defined the dipole moment with the length vector, which goes from the negative to the positive charge. And if we're just summing up all those dipole moments, it carries that same vector notion. So here, E is in the same direction as E, right? It's important to understand that. Okay, so inside the material, we have epsilon naught E plus P. And what happens even more so? Now I have these bound surface charges, plus and minus, and there was a plus charge here that was deposited from the charge, right? Or from the battery. That plus charge and the minus surface charge right on the surface, remember the plate is touching the dielectric, will cancel in a classic macroscopic sense. So this negative charge and the original positive charge that was there, they will cancel because of the bound surface charge. And that changes the potential, right? So first, before the dielectric's inserted, all of the charges leave the battery and they start piling up on the metal. They pile up on the metal until that density is strong enough such that they're pushing back, right? All these positive charges want to repel from each other, right? They're going to push back on the battery until that force is the same as the battery pushing charge back onto the plate. You get into equilibrium. But as soon as I put the dielectric in, I cancel one of those charges. And now the battery's stronger than the force of repulsion of all the positive charges, and the battery puts another charge on there, right? So this circle means that we got an additional charge due to the cancellation due to the bound surface charge of the polarized dielectric. What does that mean? That means that the capacitor that has a dielectric material in it can store more charge than a capacitor that does not. Therefore, we know the capacitance formula for a capacitor is C is equal to epsilon A over D. And epsilon, that's what this means. I get more capacity, more storage of charge, when epsilon is greater because of this cancellation effect.
How should we think about the conductivity or resistivity of the dielectric? Like we have,
We'll get there. We're gonna add a imaginary component. This will become a complex number.
if the charge isn't flowing, but we have virtual charge shifting.
Yeah, but there's like, say you take a piece of dough, right? You're making a bread loaf, right? If you knead the dough, then what's gonna happen is you're gonna generate heat in it, right? From friction. So that's a form of loss. So what we're gonna see is when we have AC fields and we start to oscillate these dipoles by the charge. So here's the positive charge. The electron cloud goes this way, but then the incident field is oscillating. So that thing starts to oscillate back and forth. And there's a level of friction that heats up the dielectric that we'll account for by making epsilon complex when we get to AC permittivity. Good question. Okay, any other questions? Yes.
Make sure I understand the like E and P directions. The E field is going from the positive to the negative
Yes.
from plates. And then the P vector is going from the negative to positive because it's looking at the dipole, so it's gonna be inside of the dielectric.
Yeah, the bound charge. So all of the dipoles that were induced in the dielectric, the internal ones canceled because they had neighboring ones where the electron cloud shifted down to where the positive nucleus is of the next atom down, right? So internally they cancel, but only the ends or the surfaces, they don't have cancellation. So, and that's because the dielectric is uniform, right? If I had one atom here that had, the nucleus had 10 protons and the electron cloud stretched down, the next nucleus down here, let's say it has 20 protons. So the 10 proton or the 10 electron cloud is not going to cancel the 20 proton nucleus, right, of the next atom down. So it has to be uniform dielectric. If it's uniform, everything cancels inside and only the bound surface charge exists at the ends. And from there, that means the polarization field P now points from minus to plus, from the top surface to the bottom surface. Yeah? So it's due to, but you can see electric field normally goes from positive charge to negative charge. But here the polarization field is opposite. It goes from negative bound charge to positive bound charge. And that way you can add everything up.
Does that mean the thickness of the dielectric doesn't impact if you have the same distance between the plates?
Yeah, it will for sure, right? Let's say we make this dielectric only, we insert the dielectric and it's only this thin, right? If it's only that thin, then you won't get as strong of a cancellation effect, right? Still, you'll still have some charge minus here, right? That minus this positive charge will terminate on this minus, and then you'll generate a bound surface charge plus that will terminate on this minus, and you'll still get some cancellation, but not nearly as strong, right?
Because the dipole vector is not as long.
Yeah, you could think of it that way too. The E is not the same length as the P, right? Good.
We have a dielectric that can conduct charges.
We'll get there. That's loss.
So, is it necessary, I mean, in every single case, the direction of the polarization vector is the same as the electric field vector? Or is there any case where it is not in the direction?
Yeah, so when we get to anisotropic materials, there will be a different relationship. So look at here. D is this direction, right? Here's an equal sign. So whatever is on the right and left side must be exactly equal. And I have P here and I have E here, right? Epsilon is nothing but a constant. So E and P have to be in the same direction as D, right? There's no minus here. That's one way to look at it, right? But if I have, actually a better way to look at that is, oh no, that's fine. So, okay. But when we get to anisotropic materials, D is going to equal to epsilon dotted with E, where this is called a dyadic quantity. We'll get to that. It's a tensor. So it mixes the components. Okay, good. All right, so we're almost there. We're almost to permittivity. All right, so let's define, okay, so now let's relate. So look back here on this slide. If you look back here, what do we have? Let me clean this up. If you look back here, we have epsilon naught E plus P is equal to D, right? But we want to relate P back to E so we can come up with, we can factor it out and come up with a single scalar for this, right? Still, we have to calculate P. We don't know how to calculate P, right? We just have P, we have its definition. We could probably use the definition to design some kind of apparatus to measure it. But here we have a relationship epsilon naught E plus P equal to D. The strategy is to relate P back to the applied field, which it should have some kind of relation, right? I apply an electric field here, I induce a P. So there must be some cause and effect proportionality constant there. So let's look at it. So in linear media, we expect the applied field E applied results in generally small polarization of molecules through distortion and or rotation, right? And we expect a linear response to the field for small distortions. So media that's considered linear, you've heard of isotropic, you've heard of homogeneous. Homogeneous doesn't depend on position. Isotropic doesn't depend on direction. You have dispersionless, doesn't depend on frequency. And then you have linear media, meaning it doesn't depend on the strength of the applied field. If I hit this thing with, megavolts of electric field, it's going to cause nonlinearities, right? But if I hit it with a small electric field, then we can assume that there's a linear response to the field. Linear, what do we mean by linear? P and E are related by some constant, right? A proportionality constant. How much P do we get for a given applied electric field strength? Well, that's characterized through this constant called the electric susceptibility, and it's a proportionality constant. We multiply by epsilon naught. So if we do that, okay, so here's a note. The larger chi E means a large response to the applied field, and the medium is easier to polarize. Okay, so using the above, we can write D equals to epsilon naught E plus P, right? As epsilon naught E plus epsilon naught chi E into E. Now we can factor out the E because we've related everything to the applied electric field. We have this new quantity epsilon naught into 1 plus chi E. We call this the permittivity relative to free space. That's what the R means. Epsilon naught R or epsilon R. And we lump these two into the permittivity that we assign the material itself, right? Because epsilon R is a relative to free space. It's a number. It's like quantization. 10 free spaces, 2.2 free spaces, right? 2.2 times the permittivity of free space. So the actual permittivity is epsilon R into epsilon naught. All right, good. So now we have defined permittivity, epsilon. So everything is now resting on what is epsilon of the material. That gives us the relationship to P through the applied field in chi. Then once we have P, we can define the volume and surface charge densities. And that accounts for the potential due to the polarization field P, which we defined as to the sum of dipole moments per unit volume to account for the polarized dipoles, the field due to all of them. So the field due to all of the polarized dipoles, before we said we needed to sum them all up, they're all dipoles. We know how to calculate the field, the potential due to a dipole. We had to sum up all of the dipoles to some observation point to get the actual permittivity there, or scalar potential there. But instead of doing all that, I have defined this fudge factor epsilon, and that allows me to account for all of those dipoles. That one number is the same as summing up the dipoles of all the induced dipoles in the material. So this quantity epsilon is typically a measured quantity, and it's provided by high frequency material vendor like Rogers Corporation if you buy substrate from them, or you have many ways to measure the permittivity of any material that you have. Measure the permittivity. Okay, it can be calculated by modeling the dipole moments through atomic polarizability. Okay, so say you want to calculate instead of measure. Well, you can model each of these atoms through the atomic polarizability, alpha. So how well does a material polarize with respect to what is the dipole moment given an electric field strength? Well, that proportionality constant is called alpha, right? Because all we said was we have dipole moments, but we didn't relate the dipole moments themselves back to the applied field. We started with the dipole moments. So here we have P is alpha E local, right? So alpha is a proportionality constant of the polarization or the dipole moment, one atom due to applied electric field. But you'll see I've added this local here at the bottom where E local is the local electric field defined as the applied field plus the field due to all other dipoles in the medium in the crystal. So I have some kind of material media. We're going to see that later at the end of this lecture, what I mean by local field. But here's an atom. What is the actual electric field polarizing this? The incident field, E applied, plus every other atom in the entire material media polarizes and generates its own field that this atom experiences. All of them, right? So that's a difficult calculation. Yes.
We have epsilon based on an omega. So we have a variance frequency.
Yeah.
Is there a duality between space and time? Or if it's more defined in frequency, we're less defined in where it's actually happening in space?
Yeah, you mean like, okay, so there is a convolution operation that relates the two, right? So multiplication frequency domain is convolution of the time domain for permittivity.
It's sort of in the time domain, but we get less defined in space.
Yeah, I wouldn't want to say that yet. So let's hold off on that. There is a relationship between time domain and space domain. But remember, everything that we're learning in this class is time harmonic electromagnetic fields, right? In time harmonic electromagnetic fields, we're assuming we're in sort of the phasor domain where we are working with sinusoidal exponent or sinusoidal temporal variation, right? Sinusoidal temporal variation. And therefore, we don't consider time in general. We factored it out of the Maxwell equations. We're working with spatial dependent Maxwell equations only, right?
Spatial D vector that has every frequency of every point in space.
We're only working with one frequency here, omega, right? One frequency, it's in with respect to time, right? Okay, all right. So the dielectric constant, it has been shown that when a material is subjected to a static electric field, the centroids of the positive and negative charges are displaced relative to one another, forming a linear electric dipole, right? That was the first thing we thought of, or the first thing that we studied. When a material is examined macroscopically, the presence of all the electric dipoles is accounted for by introducing an electric polarization vector field P. So we have an electric vector field P here that accounts for all these dipole moments. Ultimately, the static permittivity, we're still talking about static excitation. Static permittivity is introduced to account for the presence of P, and new vector field D is defined to account for the field due to the polarized dipoles and material polarization. And we define that new vector field D as epsilon naught E plus P, and we were able to whittle that down into epsilon naught, epsilon static into E applied. So D was not a physical field, right? The physical forces of electromagnetics is the electric force field E and the magnetic flux density B. All right, so here's permittivity of a bunch of different materials, the relative permittivity, static. So you can take a look at those. All right, let's study the parallel plate capacitor a little. So here's the thing I was talking about with the adjacent dipoles. Here's a material that we've polarized, right? So this is a uniform material. We polarize it with a static electric field. And what happens inside? We have E applied. Here's two neighboring atoms. One is polarized such that the electric field is pointing down, right? So the negative charge goes in the opposite direction. And the neighboring atom has the same distortion, but the positive and negative charges are assumed to be overlapping in a classical macroscopic model, and therefore those cancel. So what does it leave? Just the surface charge density on the surface of the material. So here we have polarization field P because it's a uniform material. All these internal cancellations happen. Only the plus and minus charges remain. You get a minus charge density on the surface and a plus charge density on the opposite surface. The polarization field P goes from minus to plus charges, and we're left with only a bound surface charge on the upper and lower surfaces, right? Okay. We already talked about this, right? I guess I jumped ahead. So what's happening here is we end up with the presence of the dielectric allows these two to be canceled as well from the battery, and the battery puts more charges on there. Okay, so we talked about this, right? Yes.
D that we're talking about calculating, where is that value for?
Everywhere. Epsilon naught.
Outside of the capacitor?
Yeah, look here. So it has D exists everywhere. Outside of the capacitor, the electric field is still there, right? It's assumed to be there. It might be 0 outside, but it's assumed to exist everywhere, right? P is 0 outside of the material if it's in vacuum, right?
Right, but so then, I guess, so then when you're outside, you use like a different constant, like you have to make sure that you're using the epsilon for
Oh, yeah, great.
material.
Here, right? Yeah, epsilon is equal to 1 outside of the material, right? Free space is 1 E naught, because epsilon naught is the permittivity free space. So epsilon S is 1 outside the material, and it will be a different value inside, maybe 4, right?
So it might be like discontinuous.
Oh, yeah. Good question. Okay, so we talked about this. So what different ways are there to polarize material media, right? There are multiple different polarizations. The first one we studied is called electronic polarizations. The distortion due to the atoms that comprise the material and their electron clouds get distorted, right? There's also ionic or molecular polarization. I could have some kind of ionic bond like sodium chloride, and by applying an electric field, I can distort that bond. So this is for a molecule, right? Ionic or molecular polarization. It distorts the bond between two different elements, right? These are elemental. And then we have dipole or oriental polarization, meaning I could have a material like water. Water has a static electric dipole, right? Every H2O molecule has an electric dipole moment associated with it. Water's polar. And they are pointing in all different directions due to thermal agitation. But when I apply a field, I cause all those water molecules to rotate in a line. Okay, good. All right. So let's do a quick example. So we have, okay, so before insertion of the dielectric slab, we want to determine A, the total charge on the upper and lower plates. So here's the problem we're trying to solve. 64 centimeter squared upper and lower plate areas. We have the separation is 4 centimeters. We insert a dielectric material of epsilon r equal to 2.56 in between the plates on the right half, and the battery that's connecting the two plates is 8 volts. So this should be a volt. I don't know why we need a volt here. Okay. All right. So we use a capacitive definition before we insert the dielectric slab of Q equal to CV, which is epsilon naught A over D into V, right? Because C is epsilon naught A over D. And we calculate epsilon naught is 8.854 times 10 to the minus 12. We know that the area is 0.08 squared and the battery is 8 volts. And we divide by the separation to 4 centimeters and we get 1.1 times 10 to the minus 11 coulombs. All right. We could have also done the same calculation using Gauss's law. So we know that E applied is equal to E divided by D by definition, right? This is the electric field. Wait. Yeah. That should be V. Yeah. No, V divided by D, right? That should be a V. V divided by D. Good. 200 volts per meter is the electric field strength. Okay, good. Now we integrate over the upper plate. So this is a closed volume or closed surface integral over the upper plate only. So we go like this and back there, right? So that surface, if we integrate over the upper plate, d dotted with ds, we're going to integrate from minus 0.04 to plus 0.04 because this has an 8 centimeter distance and it's also 8 centimeters in this direction. So there should be a minus sign here too as well. Jeez. Okay, so minus 0.04 to plus 0.04. Epsilon naught EA is D. And because there's nothing in we're talking about the capacitor before we insert the dielectric slab, dotted with Z dx dy. If you do that calculation, you get the same number. You should, because we're talking about actual charges on that plate, right? Or you could use the boundary condition. There's another way to do it, right? Because we know that N dotted with D1 minus D2 has to equal to the surface charge density. And we're trying to calculate the surface charge density. So epsilon naught E1 is, so we're assuming, okay, so N times rho sub S. So the normal component of rho sub S, okay. It's kind of a poor way to write that. So epsilon naught E1 is D1. And we're saying that forget about D2 because we're talking about in the material, right? We're assuming this plate has some thickness. So we're talking about the interface on the upper surface of the upper plate. And this n, I'm not sure should be there. It can't be, right? Because the left side is not a vector. This is not n, so get rid of this n. It's another copy and paste error. I made all these notes over the summer. It took me some time. Okay, so copy and paste error. Should be epsilon naught E1 equal to rho, right? Because n dotted with D1 is E1, let's say, the normal component of E. And then we have epsilon naught D2 is 0. So then we have epsilon naught V over D. We know the definition of E. And that's equal to rho sub s. Then we have epsilon naught V over D into A, because we multiply both sides by A. And rho sub s times A is Q. Surface charge coulombs per meter squared times A in meters squared, we get Q.
So earlier we had to sigma S says the
Yeah.
surface charge is related to the normal of the.
Yes, because why is that? This is PEC, right? We derive the boundary condition on PEC. Normal component on a perfect electric conductor of D terminates on the charge. There's no tangential E on the conductor based on the other boundary condition for PEC, which is tangential E goes to 0, right? So the normal component terminates on charge because there's only a possibility of a normal component of E, and the normal component of D terminates on the charge. Good. Okay. Now, let's add the dielectric. Or no, we got to calculate the total stored energy in the capacitor, which is 1/2 CV squared, a classical formula. And we can calculate what that quantity is because we know all the numbers, right? 4.5 times 10 to the minus 11. So there's a little thing up in the upper right corner. It's a bad analogy, really, I think, because electrical and mechanical energy are very different. But if you took a pencil and lifted it 1 centimeter, you would need the amount of energy in that capacitor, 10 million of those. So it doesn't hold much energy. Okay. After insertion of the dielectric slab, we calculate all the same thing, right? Epsilon A is 8 over 0.04, which is V over D, 200 volts per meter still. But now D has epsilon R in it, so 2.56. So we get more electric flux density. And the charge Q is equal to D into A, which is, now we have epsilon R. It's the same formula derived on the last slide. And we get 1.45 times 10 to the minus 11 coulombs, right? Which is more in the dielectric region, which we have more than we had before. Here's the same calculations, but in the free space region. And what you can see is, due to the dielectric, we're storing way more charge, right? An order of magnitude almost. Good. Okay, and you can do the same calculation for the energy in both regions, and you can calculate the total energy density, and what we get is almost double relative to the capacitor without the dielectric. These are all classical formulas, 1/2 CV squared, epsilon R, epsilon A over D, right?
Experiments where they levitated a frog with very strong methods.
Oh yeah, I've seen that. I can't remember how they did it though, but I have seen that.
It's just an insane amount of Teslas that in water.
Yeah. Yeah, that's it. That's an interesting. I do remember that though. I have seen that. Good. Okay. You guys can read through that. Let's get to some fun stuff now. We've been talking about statics. Statics are kind of like, that's what is always hard about teaching electromagnetic theory to students. Statics, you have to get them through it because it's not fun. There's no dynamics, there's no waves, right? So it's hard to motivate it. But when you get to dynamics, things become super fun. So let's get to dynamic polarization now, dynamic permittivity. Here, we're gonna go back into a little bit of study of differential equations first, and make an analogy between a differential equation that you've solved before in your life, right? So we have an applied electric field is 0 for the upper row, right? The electrical equivalent is a mass M, which is the nucleus, right? And we have charge Q. So there's a nucleus, and then the negative charge is assumed symmetrically distributed around the nucleus, and those two charge densities are equal and opposite, so they cancel and give you no dipole moment induced, right? Same thing we've seen before. What is that in a mechanical equivalent? We have a mass. The positive mass is fixed, the positive charge, positive side of the mass. And then there's the negative charge, which is free to move, right? Which is attached to the mass. But nothing is moving because there's no applied electric field. I then apply an electric field E naught. That electric field causes a dipole moment. The vector L goes from the minus to the plus charge, as we saw. The mass M associated with the positive charge, capital M, and the mass little m associated with the minus charge have now separated, right? And here we have the mechanical analogy. We have the mass M associated with the minus charge is now separated from the positive charge location. And there's some level of a spring distortion, right? It's like stretching the electron cloud. If I turn off the electric field, that electron cloud is going to go back to being symmetric. So it's like a spring stretched. So I can model it in a mechanical analogy using a spring of spring constant S. There's also some friction due to this platform that the mass M is sliding on that is not perfect, all right? So it has some friction with coefficient of friction, a damping coefficient of D, all right? And it's displaced the distance of L, the same distance. All right, good. So the third bullet is third part in the cycle. So we're talking about AC excitation now. The applied field is oscillating, all right? So first it pulls it to the left, then it goes back to its equilibrium position, then it pulls it to the right, right? There's some damping here and some spring constant that holds it back, right? So you know the differential equation for this is written up here. M d2L dt squared plus d dl dt plus s into L is equal to Q into the electric field with the function as a function of time, which we know we can model as E naught into e to the j omega t. All right, so you've seen this differential equation, right? M d2x dt squared. So let me write it like this, maybe it'll look more familiar. M d2x dt squared plus, what do we normally call the damping? C, right? C dx dt plus k into x, which is the Hooke's law, and that's equal to some force that you apply, right? As a function of t. So that's the same differential equation, right? Okay, good. Great. So let's see what we do here. Let's divide through by m. So to get to this line, we divide through by m. All right. And then to get to this line here, we're going to define d over 2m as some constant called alpha. And then we're going to define s over m, the square root, as omega naught. These are very important numbers, right? And from there, we can study the different solutions to this general differential equation based on these two parameters, alpha and m. So there are three cases, which I'm sure you remember: overdamped, critically damped, and underdamped. And we'll study these on the next slide, right? So whenever the system is overdamped, that means alpha overpowers the natural oscillation frequency, the resonant frequency, right? There's so much loss that the system is overdamped. So that's this green line here. It starts out as a displacement of 1. You stretch this thing out to 1, and then you let it go, and you watch the dynamics, the oscillations, right? It goes down to 0. There's no oscillation, too much damping. When it's critically damped, alpha is equal to omega naught, you get this sort of rapid decay, maximal decay, right? It goes down as fastest, and it stays 0. When it's underdamped, there's not as much loss, there's not enough loss, so it starts to oscillate and slowly goes to 0 as energy is dissipated in the loss, right? That's this case, it oscillates. It oscillates, but some energy is lost due to friction and then eventually comes to 0. Underdamped, yeah? Steady state. Yeah, so you mean no, right? Steady state means it's that way for infinity, right? Eventually all the energy will be dissipated. Unless your source is always inputting energy. That is one case where you can have loss, but you have steady state solutions. The source has to also continue to oscillate. Here we're talking about, I'm gonna pull this thing over to 1 and let it go. So we stretch it out to we stretch out to 1 and we let it go, right? Yeah, we'll see that next slide. Great. Okay, so let's look at that a little bit more in detail, right? Here's the theorem on the left-hand side first. We need to understand the difference between a general solution and a particular solution. and what is called a complementary solution. And the way we do that is, this is from differential equations. I'm sure you've taken this course and seen this before, but I've repeated it here. So if y is equal to y1, so the solution to the differential equation is y. There's two solutions, y1 and y equal to y2 are solutions of the inhomogeneous ODE, meaning the right-hand side is not zero, it's a driven problem. Then y equals to y1 minus y2 is a solution of the corresponding homogeneous ODE. A super important theorem. So if I have two solutions to the inhomogeneous ODE, which is the driven problem, and I take the difference of those two solutions, then that is a solution of the homogeneous ODE, where the right-hand side is zero, and I'm just looking for natural modes, right? Eigenfunctions, eigenvalues. So how do we prove that? Here is the differential equation we're considering, ay double prime plus by prime plus cy equal to g of t. If y is equal to y1, then we can say that we can replace y with y1. So ay1 double prime plus by prime plus cy1 equals g of t, right? For y equal to y2, we do the same thing. And now we're going to subtract these two equations. And we have, if we subtract them directly, we get this, right? If we subtract them, both the solutions to the differential equation here for y1 and y2, they had the same driving function. So now the right-hand side goes to zero. And we have a differential equation, and because the linearity property of the derivative, we have a differential equation in the solution y1 minus y2, the solution to the homogeneous differential equation, right? Why is that important? Because if y equal to y1 minus y2 solves the homogeneous ODE, which is easier to solve, this implies that if a single solution y2 to the inhomogeneous ODE is known, right? Then the general solution to the inhomogeneous ODE can be expressed as y1 equals to y plus y2. And we can say the general solution here is y equal to yc plus y. Okay, so so the general solution, y, is equal to the summation of the complementary solution plus a particular solution, which is steady state response and transient response. The complementary solution we can get from solving the homogeneous differential equation. The particular solution, we have to solve the inhomogeneous, right? You've probably seen this before. Okay, let's try it. Let's calculate. So here's our differential equation here. We have the complementary solution. We're going to first find the complementary solution. So that's when the right-hand side is equal to zero. So, okay, we get rid of the right-hand side, and we have a bunch of linear derivatives. They have constant coefficients, which is super easy to solve in differential equations, because if it's a linear differential equation and all the coefficients are constants, then you can just try e to the something solution, right? So let's try e to the RT, all right? Then we can differentiate. L prime of t then is r e to the RT, and r double prime is r squared e to the RT. If you plug all those back into the differential equation, then you can cancel out all the e to the RTs. That's why we chose an exponential trial function. When you do that, you're left with the algebraic equation with the constant coefficients. You can solve that for what this r was that you assumed in your initial solution. R1 and 2, it's a quadratic equation. There are two r's. So there are two solutions to this second order differential equation, and they are e to the r1 and 2, where this is r1 and 2. Okay, so now we can look at what these three cases were, right? We had, first off, on all three of these cases, this complementary solution is transient and decays to zero as t goes to infinity, right? Because we have e to the minus alpha. If alpha is not zero, then e to the minus alpha plus or minus this term here will go to zero as t goes to infinity. So it's a transient response. There is a steady state solution left over, and that's our particular solution that we want to study. Let's get the particular solution, okay? So how do we get the particular solution? We use the method of undetermined coefficients. Here's our differential equation again, but now we're going to solve for the driven problem. So we're going to try an exponential solution. Okay, so the method of undetermined coefficients, you try a trial function, you differentiate it a bunch of times on the left-hand side, you have that function on the right-hand side, hopefully you can cancel it out again. In this case, we can, it's exponential, right? There's a way to sort of guess what your right-hand side should be given or what your trial function should be given the right-hand side. But anyway, here is the solution. We're going to try L naught e to the j omega t. We can differentiate it once and twice. This should be an L. It's a lot of copy and paste errors. Okay, we divide through. So we take these and plug them into the differential equation. We can divide through by e to the j omega t. We get rid of the exponentials. Then we have a algebraic equation for the unknown coefficient L naught. L naught is our displacement, right? Remember, how far does the electron cloud stretch? This is our L. This is our L. How far does the electron, the dipole moment, remember we needed that number. The dipole moment's dependent on the length. So L naught we solve for here now. We can substitute A equal to D over 2M and we can simplify it. We get this expression here. At steady state with a sinusoidal excitation, we get sinusoidal displacement because the linear, right? At some, it can't add new frequencies or change the excitation anyhow. At some frequency omega, the coefficient is a complex constant. So E naught e to the j omega t. The displacement is proportional to the e to the j omega t, same oscillation frequency, proportional to the incident field strength, but it has this coefficient now, and this coefficient is super fun to study because that coefficient has all these new properties. This displacement, what happens when there's no loss? For example, no loss means that D goes to 0 because D was the friction coefficient of the platform and the mass. If D goes to 0, then we just have this, right? If we just have that and omega is our variable, this should be omega. All right, another error. My gosh, this should be omega. If omega goes, or no, it could be T. I'm sorry. Should be T and omega, really. There is a j omega t there. Whoops. Okay. If there's no loss, then D goes to 0. And if omega is equal to omega naught, then our displacement goes to infinity. That's resonance. That's what the definition, that's why omega naught was called omega naught. It's a resonant frequency. Remember, we derived that from the differential equation. When we are operating at a frequency, at the resonant frequency, the displacement goes wild and goes to infinity. Of course, it can't go to infinity. There's some loss that will always appear, right? And it will prevent it from growing anymore. But at the resonant frequency, every little bit of energy you add into the system adds to the previous sum. So if you have a kid on a swing, I push them a little bit, they swing and then they come back. I just add a little tiny tap, another displacement, right? Another force, they go further. I add another little tap at just the right time and they go further. So what's happening is all of my small inputs are adding up in phase at the resonant frequency to displace very largely.
You say an electron is resonating around a proton. Or it's kind of oscillating around this. So the electric field is
Okay, yeah, let's talk about it right after the class, yeah? So the class, it's over now, right? So, okay, come to my office hours if you have questions on the homework. Go over these slides a little bit, and we're gonna continue, from this discussion next lecture, all right? Good, all right, see you guys. Yes, what's up? Okay. Okay.
Can we, on the other side of the equation, it has this thing.
Yes.
But can I the solution of this nonlinear equation, has some sinusoidal form too, some of two sinusoids, 3 of them, 4 of them. Can I do that?
If it's linear and you excite it sinusoidally?
No, it's not.
Nonlinear. Yeah, in that case, when you solve a nonlinear differential equation, typically what you do is you linearize the differential equation around stationary points.
Okay.
And then you solve for what's called the phase plane and so forth.
Okay.
I think so. maybe you could expand it in terms of multiple frequencies that are generated due to the nonlinearity. You probably could
We
have used.
don't have multi-frequency. The excitation is just one frequency.
But it's a nonlinear
single
medium.
tone. The system has some nonlinearity.
Yeah.
So the differential equation has nonlinear form, but can I like imagine that I has some like form of sinusoidal, so like summation of some sinusoidal with different frequency and put it in that nonlinearity and solve the equation, or should I like solve it numerically?
I think you can do that. There's an approach called harmonic balance. I think is what you're talking about.
Yeah, harmonic balance is not like efficient, I think, in steady state or in transient.
Maybe transient. I'm not an expert in nonlinear differential equations. I've taken courses, so I know things. But I have to look at it and we have to sit and think about it, solve it together, I guess.
Yeah.
Luckily, a lot of things we do in motion basis.
Yeah.
And that allows us to do all. Linearity is best, but if you have nonlinear components, the way I see it is you expand functions to a certain number of harmonics to generate the nonlinearity, and then you solve the system by assuming ground. That's right, on balance.
Yeah. I think I thought, okay, I have this voltage source that is sinusoidal. If it was like current source, that might be different. I can do that, but when I have this voltage source that it's on other side of the equation, I can't like assume that the solution also has that form. I'm not going to do that. Yeah.